So today we're going to talk about the last piece in chapter 4.1, and I just wanted to remind us, so this first piece right here, the limit as h approaches 0 of f of x plus h minus f of x over h, is our definition of f prime of x. We call it the limit definition of the derivative, and what we get out of this particular thing is we actually get an equation for f prime, and then we can just figure out the derivative anywhere by plugging in our own x. Now, I didn't actually do examples of these. The book just barely touches on these, but these are also, now the first one is just a slightly altered formula of the first one, and these, so what I get out of this is actually a function, right? What I get out of this is actually a specific number. So if I was just looking for f prime at one specific point, it would be perfectly acceptable for me to use either one of these formulas. Now this one here, it's just being replaced with, I'm just replacing x with a, and everything is identical, so it makes sense in this case it's f prime of a. Now this one here, this f of x minus f of a over x minus a, the limit as x approaches a. So we do get 0 over 0 again, it's indeterminate form. And this one is the one that we're going to talk more about today, because this is good for talking about whether a graph is differentiable or whether it's a function is differentiable at a specific point. So we're going to use this one today to talk about the relationship between differentiability and continuity. Okay, and so if f is differentiable, then the derivatives from the right and the left exist and are equal, right? And the derivatives are limits. So what we want to look at in some cases here are some limits from the left and right. We're going to use this particular formula. We're just going to talk about this for a moment. Okay, so our first function that we want to look at is f of x equals the absolute value of x minus 3. And I want us to look at the derivative at, what I'm looking at is, I want to look at f prime of 3. Okay? I'll explain why specifically I want to look at that, but I'm going to use this formula, the f of x minus f of a over x minus a. Okay, and so we're going to use x is 3. So we're going to set this up, and it's going to look like the limit as x approaches 3, because this is as x approaches a, of f of x, which is x minus 3, minus f of 3. So when I plug in 3 here, right, so this is, my a is 3, so f of 3 means I'm going to plug in 3 here, and I get 0 over x minus 3, x minus a. Right, you see the relationship. This is this formula using this f, I'm taking it from this. Okay, so I'm going to look at this. So I can drop the 0, right? There's no point in me looking at that. So the limit as x approaches 3 of the absolute value of x minus 3 over x minus 3. Now with a little, so I'm going to look at the limit from the right and the left. So, right, and the limit as x approaches 3 from the left looks like this. Okay, so I'm going to look at these separate. If my function is differentiable at x equals 3, then these two limits, right, should be equal, and they both should exist. All right, so when I look at 3 from the right, so that means I'm going to plug in values slightly larger than 3. Right, I'm just going to pick an integer here, 4, for instance. If I plug in 4, then I get 4 minus 3, which is 1, over 4 minus 3, which is 1. So I get 1 over 1, and I end up with 1. And so you can try other numbers right up close to 3, but I'm always going to get out 1 as long as I'm choosing a value for x that is larger than 3. Now when I go in the opposite direction, for instance, if I choose a number smaller than 3, then I get 2 minus 3, which is negative 1. I take the absolute value and I get positive 1, but then I still have 2 minus 3 down here. And so I have positive 1 over negative 1, which gives me negative 1. Okay. If I go to graph this as well, right, then this graph actually looks like the graph of the derivative at 3 here. It is looks like this. Okay, you can try to graph it. And so that's two-sided, right? The limit from the right is 1, the limit from the left is -1. So the two limits exist, they don't just equal each other. And so my graph of the absolute value of x minus 3 is, since this overall limit does not exist and I'm doing the derivative, this is not differentiable at x equals 3. Right? A lot of times we take for granted that the limit exists or that the derivative exists in all places, but that's not the case. Okay. All right, so that's my first example of a place in my graph that is not differentiable. So let's look at another thing here. We're going to use the same formula again. We're going to use this piece here. Okay. And so I'm going to, this time, I want to look when x equals 0. So this time I'm going to have the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. All right, so this time I wrote it out separately. So now let me put my things in here now. So this is equal to the limit as x approaches 0 of f of x is x to the 1/3. F of 0 is 0, right? I plug in 0, I get out 0, all over x. And hopefully we notice that what I have here is x to the 1/3 over x. And this is where I can subtract my powers. This is an implied 1. So really I have 1 over x to the 2/3, or this could also be written as 1, or it could be written as just x to the -2/3 as well. So we're still looking at the limit as x approaches 0. I'm going to use this one here because I think it's a little bit more straightforward, that I can see right away as soon as I plug in x as 0, I'm dividing by 0, which in this case, right, I'm going to get an infinite result because I have 1 over 0, which implies that x equals 0 is a vertical asymptote if I were just looking at this. So this is another place where my derivative fails to exist. At x equals 0. I could say it's not differentiable at x equals 0. Okay. Now, if you know about these particular functions, one thing I'd like to point out is that the graph of the absolute value of x minus 3 is completely continuous, right? It's shifted over here, and it looks like this. And x to the 1/3 as well is completely continuous. So continuity is not the issue here. Right? So the cube root of x looks very similar to that. And so we're going to talk about the relationships here between differentiability and continuity. Okay? And so the first thing that we need to know is that functions that are differentiable are in fact continuous. So if you're told that something is differentiable, then differentiability applies continuity. It's very straightforward. If something is differentiable, then you can assume it's continuous wherever they're talking about. Functions that are continuous, like the absolute value function and the cube root of x, right, x to the 1/3, were continuous, but they weren't differentiable. Let me get my words right here. And these are the cases where it's not differentiable. So the thing with the absolute value was that it had the sharp bend at x equals 3. And so functions that are continuous that are not necessarily differentiable are any function that has a sharp bend. Now, it's completely differentiable everywhere else. It's just not differentiable at that bend. Okay. And so because if you want to think about it, right, because these are two lines coming together to a point, and so the derivative is really the slope at any point. Well, the slope on this side is negative. The slope on this side is positive of my graph. And so where am I putting my tangent line here, right? There's no good place for it. And so we say that this is not continuous, or it is continuous, just not differentiable here at, if this is x is 3. Okay. So any place that there is a bend, that spot is not differentiable. All right, so then we also had, right, this was f of x is equal to the absolute value of x minus 3. Then we also looked at f of x equals x to the 1/3, or we could also written it as the cube root of x, right? And the problem here, right? Up here, we found that the limit from the right and left existed, they just weren't equal. So the derivative kind of looked like a jump discontinuity. But in this case, what I ended up when I found the limit was I found that it was an infinite case. And this is the picture that I get at an infinite case. And essentially, what happens is my graph here takes on a little vertical slice. Okay, so this has a vertical piece of my graph. And essentially what is going to happen is when I find out that my derivative ends up being infinity, then that means that the tangent line is actually vertical. It's got that undefined slope. Okay, so these are both cases of places on my completely continuous graph that are not differentiable. So they are completely connected. It's just that anytime I get a sharp bend or I get this little vertical piece here, right, where my tangent line would be vertical, then the derivative does not exist there, so we'd say it's not differentiable at that point.